In this video, we're going to finish up our discussion of partition functions and look at one final concept which can be demonstrated by looking at the rotational partition function. So let's pretend we have some diatomic molecule here, and it's got some mass m1 and some mass m2 for the two atoms. They're separated by some bond length L, and they're rotating around this center of mass, which is somewhere along this bond length vector here. So the quantities of interest here are really the moment of inertia, which is going to equal the reduced mass times the bond length squared. The reduced mass is going to be mass 1 times mass 2 over their sum, mass 1 plus mass 2. And then the energy levels, which you get by solving the rigid rotor model for the quantum mechanical model system that looks like this, is going to be that the energy depends on some quantum number j, which is going to be h bar squared times j plus 1 over 2 times moment of inertia. So everything I just said there, the only important part that I want you to focus on is that there are some energy levels, and they depend on this integer j, and it starts from 0 and it goes up. So we have some set of allowed energy levels here. And h bar, in case you haven't seen that before, is just Planck's constant divided by 2 pi. Okay, so we've got this energy levels that go up quadratically with this integer j here for the allowed energy levels of how this molecule can rotate. So we want to get our partition function for these given energy levels here. But there's one more caveat that we need to look at, and that is the concept of degeneracy. So for each given value of j here, there are going to be 2j plus 1 states at that energy level. So at j equals 0, there's 1 state. J equals 1, there's 3 states. J equals 2, there's 5 states, etc. And it just goes on and on and on. So this g of j there is going to be called a degeneracy factor. It tells us at a given energy level how many equivalent states are there with that energy level, with that value of energy. So we need to modify our equation for the partition function very, very slightly when we know we have degenerate states like this. We have Q is still going to be a sum over all of the states. So if we have some index j, but now instead of just being the Boltzmann factor, e to the minus ej over kbt, or equivalently e to the minus beta ej, we also need to insert this degeneracy factor in front here, g of j. So in our sum here, there's going to be a multiplication of the number of states with that energy level times e to the minus beta ej, or e to the minus ej over kbt. Those two things are equivalent. Okay, so for our rotational partition function, if we have all of our Boltzmann factors there that we want to sum over to get it, what we are going to have is that our rotational partition function as a function of temperature, and again, remember this is going to be for a given diatomic molecule, so let's just remind ourselves that this is for a diatomic molecule. You can't rotate if you're monatomic because there's nothing to rotate around, so this is the case for a diatomic molecule. So it's going to depend on temperature for its rotational partition function. That's going to be a sum of all of our Boltzmann factors, so from j equals 0 up to infinity. Then we have our degeneracy factor of 2j plus 1 times our Boltzmann factor, e to the minus beta, remember 1 over kbt, times the energy level. And the energy level is h bar squared j times j plus 1 over 2 times moment of inertia, this reduced mass times bond length squared. Okay, so that's the sum. So we need a way to evaluate this sum. And as long as we're not at very low temperatures, typically many rotational states are occupied near room temperature. And as long as we're at temperatures where a sufficiently reasonable number of rotational states are occupied, That could be a few to many dozen states that are occupied for a typical molecule at room temperature, and that's just going to depend on what this moment of inertia is relative to this beta, to the temperature. As long as we're at a high enough temperature, we can approximate this sum again by an integral. So what we're going to do is approximate this sum as the integral from 0 to infinity with respect to j of 2 times j plus 1 times the Boltzmann factor e to the minus beta h bar squared j times j plus 1 over 2I. Okay, so in order to evaluate this integral here, we're going to do a substitution. That substitution, you might guess, is that x is going to be j times j plus 1, as we see up in the exponent here. And then, taking the differential of that, dx is going to be 2j plus 1. If you take the derivative of j times j plus 1, you'll get, this is j squared plus j, which the derivative of that would be 2j plus 1. Okay, and then 2j plus 1 times dj. So to complete the substitution, we have that our dj here is going to equal dx over 2j plus 1. So substituting back in, we're going to have that q is going to equal the integral from 0 to infinity. When we substitute the limits for j equals 0, we get x equals 0. When we substitute for j equals infinity, x equals infinity. So the limits stay the same. Integral from 0 to infinity dx times the 2j plus 1, which was there, divided by the 2j plus 1 in the dj substitution. So that nicely cancels out for us. So this prefactor here is going to be gone. And then we're just left with our exponential. We have e to the minus beta h squared j times j plus 1 is just equal to x over 2I. So really what we have here is we need to find the appropriate integral from 0 to infinity of, let's say, dy, just to make it easier, of e to the minus, let's say, alpha y. Okay, so if we're going to do that substitution there, then this integral, if we evaluate that definite integral there, is going to end up coming out to be just 1 over alpha. If you substitute that integral and actually find the analytical result. So what is the alpha that we have? Our alpha is whatever we have times x. So if we go down to our integral here, we have beta h squared, and this is h bar squared. I want to note. Yeah, I kept h bar everywhere else. Okay, so we have beta h bar squared over 2I. So writing that down, we have our alpha equals beta h bar squared over 2I. So 1 over alpha, or the result of our integral, q, is going to be 2I over beta h bar squared. And since we have this h bar squared here, we know that's h over 2 pi, so 1 over h bar squared is going to be 2 pi over h squared. So there's a 4 pi squared we could substitute up in the numerator here. So we could equivalently multiply this by 4 pi squared and get 8 pi squared I over beta h squared. Okay, and if just for good measure, if we want to substitute in beta, reminding ourselves that beta equals 1 over Boltzmann constant times temperature, we have a beta on the denominator, So that means we have a kBt on the numerator. So our final result for our rotational partition function is going to be 8 pi squared I kBt over h squared. Okay, so now we've calculated another partition function. It's straight from the Boltzmann factors, which came from the energy levels, and now we add the extra caveat that we had degeneracy to take care of, and degeneracy just comes into the early part of this Boltzmann factor. We just multiply our Boltzmann factor for that energy level times the number of degenerate states that we have. And then we just went through and did the same evaluation. We get this nice closed form result for our rotational partition function, assuming that we have a sufficiently high temperature and we're not really close to absolute zero, or we're not really low relative to the value of this moment of inertia.